Look at the sun right now. Just look at it. 2 sunspot regions. That is all that is left. A star that just months ago was crackling with activity, firing X-class flares, launching coronal mass ejections toward Earth, lighting up the night skies with auroras visible from places that had never seen them before. That same star now has almost nothing on its surface. 2 regions. And the speed at which this has happened is the part that is making solar physicists stop and look twice at their data, because this is not a normal solar decline. The numbers say this is the fastest drop in solar activity in the modern era of sunspot observation. And when I tell you what that means, not just for space weather, but for Earth's climate, for satellite infrastructure, for power grids, for GPS systems, for the technology that the entire modern world depends on silently every single day, I think you will understand why this story is not getting nearly enough attention right now. So let me start from the beginning, because to understand why 2 sunspot regions is such a striking and significant number, you need to understand where we just came from. Solar cycle 25 was supposed to be moderate. When it began in December 2019, the official prediction from NOAA's Space Weather Prediction Center and NASA was that it would be a below-average cycle, quieter than its predecessor. Nothing to write home about. Scientists said expect a solar maximum with a sunspot number around 115. Modest, manageable, unremarkable. They were spectacularly wrong. Solar cycle 25 did not just meet the predictions, it obliterated them. The cycle accelerated faster than any model anticipated. The sunspot numbers climbed higher than forecast. And when the solar maximum arrived, it arrived with a ferocity that surprised everyone watching. In May 2024, the sun unleashed a geomagnetic storm that reached G5 intensity, the highest level on the scale. The most powerful geomagnetic storm since the Halloween storms of 2003. Aurora borealis was visible across Europe, across the continental United States, across parts of the northern hemisphere that had not seen natural auroras in living memory. People in Texas saw the northern lights. People in Florida saw the northern lights. Social media was flooded with images of a sky on fire in places where that sight had never been seen before. The sun was extraordinarily active, and now it has 2 sunspot regions. The contrast is almost hard to comprehend. So what is actually happening? Let me explain the solar cycle mechanics, because this is the foundation of everything, and I want you to really understand the machine we are talking about. The sun operates on an approximately 11-year cycle of magnetic activity. During solar minimum, the sun's magnetic field is relatively simple. Organized, orderly, sunspot numbers are low. Solar flares are rare. The solar wind is quieter. Then gradually the magnetic field becomes increasingly complex and tangled. Sunspot numbers rise. Solar flares become more frequent. Coronal mass ejections launch magnetized plasma clouds toward the planets. This is solar maximum. Then the cycle winds down again toward the next minimum. The transition from maximum to minimum is called the declining phase. And every cycle has one. It is expected, it is normal. But what is not normal, what solar physicists are specifically flagging right now, is the rate of this decline. The drop from the active peak of solar cycle 25 to what we are seeing on the sun today has been steep. Very steep. Steeper than the models predicted, steeper than recent cycle history would suggest. The sunspot number, which is tracked daily and has been tracked systematically since the 1700s, has fallen in a way that the historical record identifies as unusually rapid for this point in a cycle that was this active at its peak. When a cycle is strong at maximum, the general expectation is that the declining phase will be somewhat gradual. A strong cycle builds up significant magnetic complexity that takes time to unwind. But solar cycle 25 seems to be unwinding faster than that logic predicts. And the result is a sun that now has almost nothing on its visible disk. 2 sunspot regions. I want to talk about what sunspots actually are for a moment, because the connection between what you see on the surface and what is happening deep inside the sun is the key to understanding why this matters. Sunspots are regions of intense magnetic activity on the solar surface. The magnetic field in these regions is so strong that it suppresses the normal convective flow of hot plasma from the solar interior. That suppression makes these regions cooler than the surrounding surface. Cooler means darker, so you see them as dark spots against the brilliant face of the sun, but do not be deceived by the word cooler. Sunspots still have temperatures around 3,500 degrees Celsius. They look dark only by contrast with the surrounding surface, which burns at around 5,500 degrees. The number of sunspots visible at any given time is the primary indicator of where we are in the solar cycle. High sunspot numbers mean high magnetic complexity. High magnetic complexity means high probability of solar flares and coronal mass ejections. Low sunspot numbers mean the opposite. The sun is magnetically quiet, the field is unwinding, we are approaching minimum. But here is what makes the current situation particularly interesting and what separates this from just a routine solar decline. The transition between solar cycle 25 and solar cycle 26 is approaching. And the character of that transition, whether it comes quickly or slowly, whether solar cycle 26 begins strong or weak, whether it follows a pattern consistent with recent cycles or diverges from them, will have consequences that extend far beyond space weather forecasting. Because there is a longer pattern that solar scientists have been watching for decades. A pattern that some researchers believe we may be entering a critical phase of right now. It is called a grand solar minimum. And I need to be precise here, I need to be careful here, because grand solar minimum is a term that gets misused and sensationalized constantly. So let me give you the accurate scientific picture. A grand solar minimum is an extended period, lasting decades, during which solar cycles are consistently weaker than average. Fewer sunspots per cycle, lower peak activity, quieter solar wind, less ultraviolet radiation reaching Earth's upper atmosphere. The most famous historical example is the Maunder Minimum, which occurred roughly between 1645 and 1715. During that period, sunspot numbers collapsed almost to zero for decades. And that period coincided with what historians and climatologists call the Little Ice Age. Colder winters across Europe and North America, frozen rivers that had never frozen before, failed harvests, population stress. Now correlation is not causation. The Little Ice Age had multiple contributing factors, and scientists debate the exact contribution of the Maunder Minimum to the temperature anomalies of that period. But the coincidence is real. The solar activity collapsed, the climate cooled, and the connection between solar output and terrestrial climate, while complex and still actively researched, is not a fringe idea. It is mainstream science. Some solar physicists have published research suggesting that the pattern of recent solar cycles, the unexpectedly strong cycle 24 peak, the dramatic cycle 25 surge, followed by this rapid decline, may be consistent with the early stages of a transition toward lower overall solar activity over the coming decades. Others disagree. They say the data does not yet support that conclusion, that one rapid decline phase does not a grand minimum make, that solar cycle 26 may rebound strongly. Both positions are held by credible scientists with real data, but here is what neither side disputes. What is happening on the sun right now, the speed of this decline, the drop to 2 sunspot regions, is outside the range of what was predicted for this point in the cycle. The models did not forecast this. The historical analogs for a cycle, this active declining this fast, are limited, and that means we are in observational territory where the data matters more than the predictions. Because the predictions are already wrong. I researched the daily sunspot records maintained by the Royal Observatory of Belgium, which runs the World Data Center for the Sunspot Index and Long-Term Solar Observations, SILSO. This is the definitive global record of solar activity going back centuries. And when you map the current decline rate against the historical database of cycle declining phases, the steepness of this drop stands out, not catastrophically, not uniquely unprecedented in all of history, but notably fast for a cycle of this magnitude. That is the data talking, not speculation, not alarm for its own sake, the data. Now let me talk about what a prolonged solar minimum actually means for us, for technology, for infrastructure, for the systems that modern civilization depends on, because this is where the story moves from abstract solar physics to something that touches everyone, During solar minimum, the solar wind weakens. The heliosphere, the bubble of solar wind that surrounds the entire solar system, contracts slightly. And when the heliosphere contracts, more galactic cosmic rays penetrate into the inner solar system and reach Earth's atmosphere. Cosmic rays are high-energy particles from outside our solar system. During solar maximum, the strong solar wind deflects many of them. During solar minimum, more get through. Why does that matter? Cosmic rays interact with Earth's upper atmosphere. They ionize atmospheric particles. Some researchers have proposed connections between cosmic ray flux and cloud nucleation, between cloud cover and climate. This research is contested and ongoing, but it is real science being done by real scientists at institutions including CERN with their cloud experiment. There is also the infrastructure dimension, and this one is more immediately concrete. During solar minimum, there is less ultraviolet and X-ray radiation from the sun reaching Earth's upper atmosphere. That reduces atmospheric drag on satellites in low Earth orbit. Reduced drag sounds beneficial, but it means orbital debris, dead satellites, rocket stages, the growing cloud of space junk accumulating in low Earth orbit. That debris stays up longer, decays more slowly. The risk of collision for operational satellites actually increases during solar minimum because the natural atmospheric sweeping mechanism that pulls debris down is weakened. We have more satellites in low Earth orbit right now than at any point in human history. SpaceX, Starlink alone, has thousands of satellites operating in low Earth orbit. The collision risk environment during this solar minimum will be different from any previous minimum simply because of how much hardware is now up there. And during solar maximum, the concern is geomagnetic storms damaging satellites and power grids. During solar minimum, the concern shifts. Less flare risk, but more cosmic radiation exposure for astronauts and high-altitude aviation. More orbital debris persistence. And the slow, quiet, but real influence of reduced solar output on the upper atmosphere and potentially on climate. The transition between these two risk profiles is happening right now, and it is happening faster than expected. I also want to address something that a lot of people are going to ask about, the auroras. Because aurora visibility became something of a cultural phenomenon during the peak of solar cycle 25. People in unexpected latitudes saw the northern lights for the first time. There were aurora alert apps and aurora chasing communities and millions of photographs shared across social media. That is largely over now. As sunspot numbers fall, as solar activity declines, the frequency and intensity of geomagnetic storms that produce visible auroras at low and mid-latitudes drops significantly. The spectacular widespread auroras that people saw in 2024 are not going to be a regular feature of the sky for a while. During solar minimum, aurora viewing returns to being a high-latitude activity, a privilege of those who live in or travel to polar regions. The sky show is winding down, and the sun that put it on now has 2 sunspot regions. So what do we watch going forward? This is always the critical question. Does the sunspot count continue to fall towards 0? A sustained period of 0 or near 0 daily sunspot numbers would mark the beginning of the solar minimum proper. Scientists will be tracking the date of that transition carefully because it anchors the timeline for when solar cycle 26 is expected to begin. What does the early character of solar cycle 26 look like? The first new cycle sunspots appear at high solar latitudes and have reversed magnetic polarity compared to the old cycle spots. Spotting those first new cycle regions is the signal that the next cycle has begun. The timing and intensity of that emergence will tell scientists a great deal about whether cycle 26 will be strong, weak, or somewhere in between. Are there any signals in solar magnetic field measurements suggesting what cycle 26 will look like? The polar magnetic field strength of the sun near solar minimum is one of the best predictors of the next cycle's intensity. Scientists are measuring those polar fields now. The readings will inform the cycle 26 predictions. And are any research groups publishing updated analyses of whether the current decline pattern is consistent with a transition toward lower long-term solar activity? Because that question, that grand minimum question, is going to get louder as the data accumulates over the next few years. Guys, the sun is the engine of this entire solar system. Everything about our climate, our space environment, our technological infrastructure, Our ability to operate satellites and power grids and communication systems without disruption, all of it is connected to the activity of that star. And right now, that star has 2 sunspot regions, after the most active solar maximum in decades. Declining faster than the models predicted, faster than recent history suggested it would, the sun is going quiet, and going quiet faster than it should. Whether that is the beginning of a prolonged period of lower activity or simply an unusually steep descent into a normal minimum, the answer to that question will shape the next decade of space weather forecasting, climate science, and infrastructure risk management. I am watching the SILSO data every day. I am watching the Space Weather Prediction Center updates, and I will bring you every significant development as this story unfolds, because this is not a story about space weather for specialists. This is a story about the star that controls everything, and right now it almost looks like it is falling asleep. Stay safe, guys. Be aware. Bye-bye.